Thank you, Mario. And good morning, good afternoon, and good evening, everyone. I'm Kazuki Yoshida from Japan Atomic Energy Agency. Before going to my presentation, I'd like to appreciate all the organizers and also participants for this very nice series, for making this nice series of the reaction seminars. I'm very happy to join and present my research activities here today. Okay, so I'm going to talk about the alpha clustering phenomena and cluster knockout reactions, how we can investigate, probe those kind of structures or states through the cluster knockout reactions. So as many of you may know that there's a single particle picture of nucleus, and that is independent nucleon motion, and they are bound in a single particle orbitals and within the mean field potential made by themselves. So this is one of the typical picture of nucleus. But besides that, we know that there's a cluster states for some specific nuclei and some specific states. In this kind of cluster states, two or more subunits appears in a nucleus. And so these nucleons, for example, alpha cluster is a typical clustering. And nucleons in this, for example, alpha or good core nucleus, those nucleons are tightly bound to form these particles. And coupling between these clusters are relatively weak, and they are like molecular state of the atoms. And one thing I want to note here is that these states are not completely different, and there are actually some overlaps. So they are not; these states are not orthogonal. So this is a very one important thing. So both, I would say, many nucleus has both aspects. Okay, and so these states can be characterized by their single particle or cluster wave function, and also they are characterized by their quantum numbers, radial, orbital quantum numbers, spin quantum numbers, and how they are coupled to make a total single particle cluster quantum numbers. And one thing to characterize them is that they are a single particle wave function or cluster wave function, that is relative degrees of freedom of the nucleon cluster and the rest part of the nucleus. And their squared norm is what we call the spectroscopic factor, and which tells us how much real true nucleus can be understood in these pictures. And actually, the alpha cluster study has a long history, and one of the very important work is done by Ikeda et al. In 1968. So it's more than 50 years ago. And in this paper, they gave this Ikeda diagram. Now we call it that this is a mass versus excitation energy. And as many of you know, maybe the barium has a 2 alpha cluster structure, and also carbon, oxygen, neon, and magnesium. And let's take on this neon, for example. And these numbers shows that their excitation energies. For example, if the neon is excited to about 4.7 MeV, from above this energy, the alpha threshold is open. That means that this neon 20 system can be separated to the oxygen and alpha system. And more than that, if it goes to the 12 MeV, carbon plus 2 alpha channel is open. And what he predicted or introduced is that if there is a nuclear state near this threshold energies, there will be a cluster state like this. And that is what Ikeda proposed by this diagram. And what I want to note here is that this is not a prediction for their shapes. It's just it just shows the number of particles and types of particles. And Yes, for lighter nuclei, for light mass region, we know, for example, the triple alpha state of carbon-12, this is a Hoyle state, very important state for astrophysical aspect. And also the in a carbon isotopes like carbon-14, for example, there's a theoretical prediction that the linear chain like structure of carbon, triple alpha linear chain like structure will appear. Yes, and for example, barium case, this is barium 8, barium 10, barium 12. These are the well-developed 2 alpha cluster states with some valence neutrons working as a bond, just like the molecules and electrons. And also the halo structure is, I would say, a kind of a cluster structure. So the question here is that they're discussing about the excited states of some nuclei, but what I want to study here is the ground state property. So what about the ground state? Do we find the alpha clustering in the ground state of these nuclei? That is the question I want to answer. To do that, what I do is the alpha knockout reaction probability, and that is directly related to the cross-section, is proportional to the probability of finding alpha cluster inside this target nucleus. So an important thing here is that because this is one-step direct reaction, cluster component only in the ground state of the target is probed, and in cluster states in the excited states have little contribution to this event, to this reaction event. So this is a good reaction probe for the alpha clustering in the ground state of the target. And to formulate that, and this is a general, let's say, general equation for the differential cross-section. And we have, so you see that this is a three-body reaction, and we need a conservation law for momentum, and this is a transition amplitude. And there's a 5 degrees of freedom of kinematics, and of course you can choose freely, but what we usually choose is the first one is the kinetic energy of the emitted proton, and other 5, I would say these are the solid angles. So these each has 2 degrees of freedom. Omega 1 and omega 2 is the emitted direction of the emitted proton and emitted alpha particle. But then this is what we call triple differential cross section, and this is the most exclusive cross section in kinematics. This is the most exclusive one. And there's a kinetic factor coming from this conservation law, and we have a t squared. This is a transition amplitude squared, where this is equivalent to the scattering amplitude. And so what we have to do is this T matrix. And what we have to do is to calculate this T matrix. And to do that, what we employ is that the Dirac-Vaillant framework, distorted wave impulse approximation. It's rather easy to understand this model intuitively. And in the initial state, we have a distorted wave, scattering wave of incident proton. And this is a cluster wave function, relative wave function between the cluster and the core, and which forming the target nucleus. And in the final set, we have the residue here, and 2 emitted particles. One is proton, the other is the alpha, and these chi1 and chi2 are the distorted waves between the proton and residue, and also the alpha and residue. And important thing is the key of the Dirac-Vaillant is here that the TP alpha, this is a proton alpha effective interaction. And thanks to the high energy, actually the impulse approximation works well. And that means that we can use this we can use the proton alpha effective interaction in a free space. So that's what we use. So this P alpha is effective interaction which describes the proton alpha elastic scattering in a free space. So this is what we do. So let me repeat, these chi's are the distorted waves under some optical potentials. P alpha is a proton alpha effective interaction in a free space. These are the reaction part, and this red phi alpha is a cluster wave function, which is over of this is a true exact, I would say exact wave function of the target, and alpha and core nucleus is coupled one, and this gives the overall cluster wave function. And then this T matrix square gives the triple differential cross section of the knockout reaction. So this is the DWA framework. And then to understand that this DWA formalism, let's consider the plane wave limit. So by considering the plane wave limit, it is much more helpful to understand the basic concept of this reaction and the reaction theory. So this is a three-body reaction. So we have 2 degrees of freedom besides the center of mass motion. So this capital R and little s. And in the plane wave limit, these 2 degrees of freedom are completely separated, factorized out. And the first term is for this little s gives nothing but proton alpha, I call little T matrix, which gives the proton alpha elastic cross section. And the rest part, these distorted waves goes to the plane wave in the plane wave limit. And this is summarized into one term this way. And we can define this Q as the difference. This is the initial momentum. And these two are the final momenta of the proton and alpha. So this Q is a conjugate momentum of this coordinate R. So finally, this gives the Fourier transform of the cluster wave function. So it's very simple. This S part gives the proton alpha little t, 2-body T matrix, and the structure part gives the this capital R part gives the Fourier transform of the cluster wave function. So this is the T matrix in plane wave limit. So T square gives this matrix element square goes to the proton alpha differential cross section, and this is just this is nothing, just a square of the Fourier transform. So this is what we see in a knockout reaction, and this Q can be determined from the reaction kinematics because B momentum and observed emitted 2 particles are observed. So this Q can be simply determined from the experiment, I would say. So this Q is fixed, so we can, by changing the kinematics, we can vary this Q, and we can get Q dependence of this T square. So this is what we see in a plane wave limit. And of course, in reality, they are not plane waves, distorted, so it is a bit modified from the Fourier transform, but this is a basic concept of the knockout reaction. And yes, I use DWA and I introduced this, but there's several other reaction theories that can describe the knockout reaction. So one is a transfer to the continuum model. This is developed by Antonio Moro and his colleagues. This is using a CDCC, a kind of CDCC-like wave function to describe the reaction, and yes, they take into account the discretized continuum state by discretizing them and solving the coupled channels problem. And also, as you know, that the Faddeev theory can describe the 3-body sketching problem and solve them exactly. And there's several work for comparing these 3 theories, and they are benchmarked actually well. And these are I don't go to the detail, but these are the comparison between them. And typically speaking, it's their theory, the uncertainty coming from this choice of these theories about 8% or 10% or so. Okay, I have to mention that this is a PPN case, nuclear knockout case, but basically the reaction framework is the same for a nuclear knockout case and alpha knockout case. Okay, and what I'm going to discuss here today is that the PP alpha reaction from these three nuclei, oxygen 16, neon 20, and titanium 48. And actually, a systematic experiment has been done in rather early 1984 by Carey et al. And they measured alpha knockout reaction with the 100 MeV proton beam and with these targets. They are all stable, but oxygen, neon, aluminum, silicon, sulfur, calcium, titanium, iron, and zinc. And they measured alpha, PP alpha cross section systematically with almost the same kinematic setup. So, and I picked up these three, and I will show some result. And the first thing is the neon 20 case. So this is, we expect alpha plus oxygen 16 cluster state in neon 20 ground state. So as you see that the alpha and oxygen 16, both of them have a double magic nature. So it's not so strange to expect alpha plus oxygen cluster state in neon 20. And actually they have, in 1984, they have already analyzed their cross-section data with the DWI framework. But there was a problem using, they used simple Woods-Saxon potential to make alpha cluster wave functions. It's just a Woods-Saxon binding problem between the alpha plus oxygen 16. And they put it into the DWI calculation and scale the theoretical cross-section to the data. They obtained a spectroscopic factor of alpha equal to 0.54. So this is rather large compared to the structure theory at that moment. And it's about 0.2, so it's more than twice difference. So they were inconsistent. And what we have done in 2019 is that DWI plus, we use DWI plus AMD wave function. So one thing improved is that the cluster wave function, the alpha cluster wave function, and what we used is the AMD wave function I explain later. And another thing improved is that the distorted waves, the optical potentials, and it was very important to get quantitatively proper result to use the alpha oxygen 16 optical potential. And we need a alpha oxygen 16 optical potential very, we have to prepare it very properly. And with this framework, what we got is this figure. So these plots are the cross sections, and this solid line is a theoretical curve calculated by the DWI plus AMD framework. And there's no artificial scaling. So the this 0.26 spectroscopic factor is predicted by AMD. So this is microscopic wave function, microscopic framework. So it can predict the spectroscopic factor. So we directly use it, and there's no scaling, and we succeeded reproducing the experimental data. So let me just briefly explain the AMD framework. This is a microscopic wave function, and that is a superposition of the nucleon wave packets, and that is described by the Gaussian form, and also the spin isospin part. And AMD wave function is a Slater determinant of these nucleon wave packets with the in an interaction of cognitive T1s. Yes, and this is a basic, a very basic concept of AMD. So if the system prefers to be ordinary spherical nucleus, it goes this way. by variational calculation. And if it prefers to be, for example, alpha plus some cluster states, it goes to the cluster states. And yes, as I mentioned, one important ingredient for this reaction calculation is the potential fit by Michel et al. This is oxygen 16 alpha elastic scattering data from 30 MeV to 150 MeV. And as you see, their optical potential fit parameters gives a very nice agreement from the forward to the backward angles. And what we found is that this very valid optical potential is necessary to describe the PPR, to describe this part of the scattering wave and to describe the PPR cross-section quantitatively. So this is the Neon 20 PPR case, and why they I would say failed to obtain a proper spectroscopic factor is that the one important thing is that they use the cluster wave function made by solving the Woods-Saxon binding problem. And as you see, this red dashed line is a cluster wave function made by the Woods-Saxon potential, simple Woods-Saxon potential, and the black solid line is the AMD one. And as I mentioned, AMD takes the antisymmetrization of power principle into account properly. So alpha amplitude inside is suppressed. So alpha particle cannot be exist in a very center of nucleus, but such kind of effect cannot be treated by solving the Woods-Saxon binding problem. So the difference comes from the inner part. The spectroscopic factor differs because of this part. But the important thing is that the reaction, alpha knockout reaction, is very peripheral. It takes place only on the surface because of the absorption of the alpha optical potential or alpha scattering wave. So as you see, using these two wave function, this is what we get. This is what we get in the cross section. So as you see, they are almost the same, and it is because the peripherality of the reaction. Only these, you see, in this region they agrees very well, and because of that, the cross section is almost the same. So we have a large ambiguity or freedom in this region, and yes, so it's not a good S factor is a not good quantity to extract from the reaction cross section. So what we determine by the knockout reaction is the surface alpha amplitude, but not the whole region that gives the S factor. And to understand this peripherality of the reaction, we can make some calculation. So this is a T matrix, and this is a cluster wave function, and these are the distorted waves. So they are divided into the reaction part and structure part. And by doing the integration over the solid angle and keeping the radial part as it is, so we obtain this one, and I defined this one is D. This is what we call masking function, which shows how the reaction is peripheral. So by this definition, if it is the plane wave, if we are in a plane wave limit, this D goes to unity. So it means there's no absorption or suppression in the internal region. And this is the masking function showing the peripherality of the reaction. So I draw two pictures. This is Neon 20 PPR for 100 MeV case, and this is 400 MeV case. But basically, they are similar. And so green dashed one is a masking function, and as you see, this one means no absorption. And in the internal region, they are absorbed, and only I would say 10% only 10% of the internal region contributes to the reaction, and the heat's about 50% or 0.5, around 4 to 6 femtometers, and of course it goes to unity in the asymptotic region because we don't have any absorption, or in asymptotic region they are just plane waves. So this shows the peripherality of the reaction. And another another tool we have is what we call transition matrix density. And to introduce this, we consider the t square that is proportional to the cross section, and t is something integrated over the coordinate, three-dimensional coordinate. So t star is something like this, t star times this integral. And if we put this t star into this one inside, and if again the integrate over only for the solid angle, and define this red circle, red squared one as delta. So t square is just one-dimensional integration over this function delta. This is not the Dirac's delta function. So this is delta. So this is delta R is what we call the transition matrix density. And this one has very nice property that the real part, if we integrated it over R, the real part goes to t square, as you see. So this should tell this means that the delta R, real part of this delta R, can be regarded as the radial distribution of the cross section, because t square is proportional to the cross section. And of course, the imaginary integral of the imaginary part goes to 0 because t square is pure real. And this is the transition matrix density. And as you see, the inner part is well suppressed. So this is a cluster with functions with Saxon1, AMD1. And this is a masking function I showed. The internal region is suppressed. And this is what we get, the transition matrix density. So internal region is suppressed, and only the cross section comes from only, say, 4.4 femtometers and above. And this is directly shows that the cross section is coming from the surface. Okay, now I'd like to move on to the oxygen 16 pp alpha carbon 12 case. So although oxygen 16 is a double magic nucleus, there's some amount of the alpha plus carbon 12 component, and which is corrected by the Horiuchi-san, Wataru Horiuchi-san, within the 5-body model. So this is a 5-body model with the carbon 12 core plus PPNN 5-body framework. And then this solid line is alpha cluster wave function you get, and its spectroscopic factor is 0.1. And if I use this cluster wave function, the cross section is like this, and I'd say it also agrees well the data. And another thing is here is OCM is a orthogonal condition model. I'm not going to into the detail, but this is a rather old framework, and they are rather compact and large amplitude inside, but shorter tail. And this dashed one, OCM, only gives this cross section. It's more than 1 order of magnitude smaller. And important thing is that spectroscopic factors for 5-body model is 0.1, but for OCM is about 0.3. So spectroscopic factor is larger for this one, as you see, but cross section is smaller. And again, this is because of the peripherality. So again, we are not looking spectroscopic factor in a cross section or in a reaction observables, but what we see is amplitude on the surface region. And Now I'd like to play some game with Wood-Saxon potential, the cluster wave function made by simple Wood-Saxon potential and solving the binding problem. So there is a 5-body model line, and I generated this red band using the various range parameters for Wood-Saxon potentials. And we can make this kind of band of the alpha cluster wave function. And this band is mapped to this red band in the cross section. And as you see, so because I scale them to fit the 5-body model curve on the surface region, they are similar, but as you see that this band is, I would say, reproduce the data, but they are mapped going back to the cluster wave function. They are so much different internal region. So this figure, from this figure, we can learn how these experimental data gives a constraint on alpha cluster wave function in this way. And in this case, about above 5 femtometer is well determined by the cross section. You see that here that they are almost the same. Okay, it's 30 minutes, and this suggests us that to introduce a kind of modified spectroscopic factor, I would say new definition, new one. In that we replace the minimum value of the radius is replaced by the not 0 but some finite value. So if this is 0, this simply gives the spectroscopic factor. And here I draw is that this arming versus this modified S factor. So at origin 0, this is the S factors for these. You see these band, and as you see, this is very interesting, but they come to get together at 4.5 femtometers. So the spectroscopic, I would say, strength above 4.5 femtometer is the same for all these single cluster wave functions. And if you know well about the ANC and asymptotic normalization coefficient, which is an important thing in, for example, astrophysics and extremely peripheral reaction, this ANC asymptotic normalization coefficient can be determined. But what we see in the local reaction is something intermediate between the S factor and the ANC. It's not completely asymptotic, but it's not completely the whole region. So in this case, about 4.5 meter and above is probed by this reaction. Okay, and this 4.5 is actually very close to the point where the masking function of this reaction hits about 50%. So it's not, you see that the smooth, and it's not like the Heaviside function, but so it's not clear and clearly defined. We cannot clearly define, but maybe they have some relation. And this is still under investigation, to how we can define this R minimum from some, how we can put some clear criterion for this R minimum. All right, and also we recently studied a titanium-48 case, titanium-48, pp alpha, carbon 44. This system is interesting in two aspects. One thing is this is one of the lightest nuclei. We can expect the alpha clustering and N not equal Z nuclei. So up to calcium-40, there are 20 protons and 20 neutrons. But in titanium case, titanium-48 is stable, but N equal N not equal Z. And also above calcium, the nucleons are occupied in a shell model picture. Nucleons are occupied in a PF shell. So there's a gap in a single particle orbit point of view. And actually, we used AMD, but we failed to reproduce the reaction data. So the variational result of AMD gives this, you see, sorry, too small, but this dashed line, this is a cluster wave function. And they gives this dashed line, and it gives far small cross-section like this. And that is actually very similar to the mean field solution. So AMD gives just normal and not alpha clustered wave function. And to explain the cross-section data, we artificially put the alpha calcium 44 cluster component with the 4.5 centimeter cluster distance. And that was necessary to explain the data, but this is again artificial alpha cluster component, so there's still something is missing, and we don't know the reason. Maybe it is because of the not equal Z nuclei, or nucleons are in the PF shell, but we don't know. There's some problem, and this is, I would say, that still the open question. And okay, let me skip this one. And now I'd like to jump to the much heavier one, medium mass nuclei. And one important question is alpha clustering universal throughout nuclear chart? And here's Z equal 50, that is TIN. And because T equal 50 is a magic number, we have the TIN isotopes, many isotopes here. And one important work is done by Stefan Tippel on 2014. And he predicted the alpha particle, existence of alpha particle on the surface of tin isotopes, much heavier than the, for example, the calcium or carbon. And this is what he got. And this is alpha particle density versus radius. So above 6 femtometers, there's a tin isotopes from 108 to 132. And he predicted these alpha particle densities. And if they goes to the neutron-rich side, neutron-rich tin isotopes, because there's a neutron skin on the surface, alpha particle formation is suppressed and they gradually disappear. So this is the same thing, but integrated over the volume. And this is the number of alpha particles versus mass number of the tin isotopes. So they vanishes around here and increase if we go to the not proton rich, but if we go close to the N equal Z tin 50, tin 100 case. So and this is a very interesting work that no one had expected such kind of alpha particle formation in the medium mass nuclei, but there was a prediction. And in 2016, I made some theoretical calculation for the PP alpha reaction from tin 120. I also examined some validation of some approximation made in the DWIA, but it's a different story. And what I found in this work is that again, the reaction is of course peripheral, and in this case, only the R equals 6.0 and above contributes to the cross section of the PP alpha, tin 120 PP alpha case. And if you remember, 6 Fermis here, so it's very nice that the alpha nuclear reaction only probes this region, and internal region doesn't contribute to the cross section. So we can directly see how much alpha particles are there in this region. by looking at PP alpha cross-section. And finally, experiment has been done by Junki Tanaka and Zaihong Yang and et al. At RCMP. And we have 400 MeV proton here, and they detected emitted proton and alpha particles. And this is published in this year. And this is the result. You see this is x-axis is a mass number, and this n alpha is nothing but alpha particle numbers as Stefan Tipper predicted in his paper on 2014. And in this experiment, we only took a look at isotopes from 112 to 124. And the black dots are the experimental data and experimental cross-section. And as you see, they decrease as we go to the neutron-rich side. And this red line is a theoretical cross-section. An important thing is that I have to mention is that this is knockout cross-section is obtained by introducing the scaling factor of 0.148 or 0.15 for the imaginary part of the scattering potential of alpha. So in that sense, this line is scaled to fit the experimental data. But the important thing I would say, I believe, is that this trend, this slope along isotopes is very well reproduced. And this is consistent with the theoretical calculation by Tipel, and as I showed before. So this is the first evidence of the alpha particle formation on the surface of nuclei in a medium mass region, and also that isotope dependence of the theoretical prediction and experimental data are well agreed. Okay, so now let me summarize my talk and give some perspectives. So alpha particle is a robust subunit in atomic nuclei. So alpha particle states in the ground state were studied, investigated by the PP alpha reaction. And in light mass region, let me define it, it's lighter than +40. AMD plus DWIA framework quantitatively reproduced the PP alpha data measured by Carey et al. But for titanium-48 case, something is still missing in a reaction theory or structure theory side. And theoretical cross-section underestimates the observed data. And in medium mass region, TIN 112 to TIN 24 case, alpha formation on the surface of this medium mass nuclei has been confirmed for the first time, I'd say, and its isotope dependence is well reproduced. And for perspectives, I'm thinking about doing the PP alpha reaction, alpha knockout reaction from alpha decaying nuclei. The typical one is a polonium 21. For example, polonium 212 is a lead-208 plus alpha system. So we may expect alpha clustering on top of the lead-208 double closed nuclei. And this reaction will be a good probe for alpha formation probability on the surface of alpha decaying nuclei. So as you know that in alpha decay process, somehow alpha particle is formed, then they penetrate the Coulomb barrier, but with a very tiny possibility, but at some point they penetrate and decays. But by doing knockout reaction, we can hit these alpha particles and we can knock out this alpha particle above the Coulomb barrier, so it's free from the penetration process. And the time scale is completely different. So the decay half-life is the most shortest one is 10 to minus 15, for example, but the knockout reaction is a typical direct reaction. It's only the 10 to minus 22 seconds. So they are 7 order difference, it's about 7 order difference. So it's completely, knockout reaction will be completely free from the penetration part, and we can directly look at the alpha formation part. And also we are trying to do something on alpha to alpha reaction, because PP alpha reaction is already peripheral, surface sensitive, because of the alpha absorption effect. So if we do alpha to alpha reaction, that will be more surface sensitive. And by doing this, and maybe by changing the incident energy or or changing the good alpha emission energies, maybe we can handle somehow the peripherality of the reaction, and we can choose which region to we can tune the region we see in the reactions. And also now the deuteron-like cluster states PN correlation on the surface of nuclear or triton or maybe helium-3, such kind of cluster states, new cluster states will be interesting. But one important thing is that the alpha particle is a robust particle, so we can knock them out just like nucleons, but these particles are very weakly bound. So the treatment of the continuum states of these Phenycon systems and breakup effect and recoupling effect of them, because of the final state interactions, have to be treated very properly. And maybe CDCC or something like this, something like that will be a important framework to describe such kind of reaction. Okay, I spoke too much, but let me finish. Yeah, thank you very much.